I vividly remember the first time I saw a chief engineer from a German brand working on a prototype. We were at a private test track, and the car felt sluggish, as if it was sleepy. The engineer didn't plug in a $10,000 computer. He simply sat in the driver's seat, performed a sequence of pedal presses and key turns that resembled video game code, and suddenly the car awoke with brutal aggression. "We manufacturers program cars for the average driver who is slow and careless," he told me as he closed the door. "But the hardware always has hidden potential that the stock electronics try to suppress." That day, I realized that most of us drive crippled versions of our own vehicles. For years in repair shops, I've seen these methods kept secret because, if everyone knew about them, visits to the dealership for software updates would disappear. Today, I'm going to reveal those tricks that skirt the edge of legality, but work better than any owner's manual would dare admit. Resetting your adaptive transmission. If you feel your automatic car no longer responds with the same eagerness as when it was new, that gear changes feel heavy or slow, or that the system thinks long and hard before downshifting when you press the accelerator, it's not necessarily a sign that the transmission is mechanically failing. In the vast majority of cases, what's happening is that your transmission has a bad memory. Modern automatic transmissions, whether torque converter, dual clutch, or even some continuously variable transmission, CVT variations, use complex adaptive learning algorithms. These systems constantly monitor how you press the accelerator pedal, your cornering speed, and your overall driving style. If you've spent the last 6 months navigating heavy city traffic, crawling along, or trying to save every drop of gas with extremely conservative driving, the transmission's computer, technically known as the Transmission Control Unit, or TCU, has adjusted the clutch overlap timings and valve pressures to be as smooth, slow, and economical as possible. Essentially, you've trained your car to be a lazy, characterless vehicle. The grey engineering trick to force the transmission to forget these harmful habits is the deep adaptive reset procedure. This isn't a simple reset, it's a purge of the control unit's volatile memory. In most vehicles from the last 15 years, especially European and American makes, there's a hidden sequence that sounds like it came straight out of a spy manual. With the engine completely off, you need to turn the ignition key to the on position. That is, where all the dashboard lights illuminate, but the engine doesn't actually start. Once there, you must firmly press the accelerator pedal all the way down, making sure to press the overdrive or kick down switch that you feel at the end of its travel. Keep the pedal in that position for exactly 30 or 40 seconds. The courtesy light diagnostic trick. The vast majority of drivers panic when the check engine light illuminates and rush to the nearest mechanic, where they're often charged $50 or $100 simply for connecting a scanner and telling them what's wrong. What the official aftermarket doesn't want you to know is that many cars have an emergency self-diagnostic function built directly into the dashboard, originally designed for field engineers and requiring no external tools. This trick is considered illegal for the workshop business model because it gives you absolute control over the information before they try to sell you an unnecessary repair or a sensor replacement you don't need. In brands like Chrysler, Jeep, or Dodge, the trick is known as the key dance sequence. The procedure involves inserting the key and turning it from the lock position to the ignition position 3 times in quick succession, without actually starting the engine, ending the sequence in the ignition position. If you do it correctly, the digital odometer display will stop showing the total mileage and start projecting a series of alphanumeric codes, such as P0300 or P0420. These codes are the car's universal language for telling you exactly what's wrong. But the trick goes even further. In many Japanese models and some older European ones, the diagnostic system is activated by a jumper on the connectors, or by a sequence involving the courtesy light in the dome. By tapping certain buttons on the door switch, or the odometer reset button, the computer enters flashing mode. The engine light will start flashing a pattern of long and short pulses, a kind of automotive Morse code. For example, 2 long flashes followed by 3 short ones signify code 23. Calibrating the TPS sensor with a multimeter. The throttle position sensor, known as the TPS, is the critical component that acts as the central nervous system between your right foot and the engine's brain. Its function is to send a variable electrical signal that tells the computer exactly what angle the throttle is at, allowing it to calculate the air-fuel mixture instantly. Over the years, the extreme heat of the engine compartment and constant vibrations cause this sensor to become miscalibrated. The internal carbon track wears down, or the mounting screws move fractions of a millimeter. The result is the most hated symptom for enthusiastic drivers: throttle lag. You press the pedal, and it feels like the car takes a thought-out time before the RPMs climb. Modern service manuals will tell you that the TPS is a sealed part that cannot be adjusted, and that if it fails, it must be replaced with a new one, which often costs a small fortune. However, old-school mechanics and race car tuners know this is a half-truth designed to boost parts sales. Almost all TPS sensors have slightly oval mounting holes that allow for minimal rotation. Using a digital multimeter set to DC volts, you can intercept the sensor's signal wire. With the engine off but the ignition on, most vehicles need a reading of exactly 0.5 volts with the throttle fully closed. If your reading is 0.4, the computer thinks the throttle is less engaged than it actually is, resulting in a lean mixture and jerking. If the reading is 0.6, the system is sending too much fuel, choking the initial response. The trick is to slightly loosen the sensor's screws and rotate it with surgical precision while watching the multimeter display until you nail the exact factory reading. The fuel additive industry is a multi-billion-dollar business selling colorful bottles that promise to clean your injectors and restore lost horsepower. The harsh technical reality is that most of these products are nothing more than refined kerosene with a couple of diluted detergents that have little to no effect on hardened carbon deposits and crystallized varnish. The best injector cleaner in the world isn't sold at a gas station. It's generated inside your own engine under specific physics conditions. In the trade, we call this the Italian tuning, or the maximum load cycle. Modern injectors have microscopic orifices that become clogged with carbon residue from incomplete combustion, especially if you frequently drive at low RPMs to try to save fuel. The trick, which many consider illegal due to the speeds and noise involved, consists of taking the car to a clear highway and driving in a low gear, such as third or fourth, maintaining the engine at a constant speed of between 4,000 and 5,500 revolutions per minute for at least 20 or 30 kilometers without stopping. The goal isn't to reach racetrack speeds, but rather to keep the engine under high thermal load. By doing this, the pressure in the fuel rail rises to its maximum, and the temperature at the injector tip within the combustion chamber reaches the pyrolysis point. In this state, varnish and carbon deposits soften and are pulverized by the massive flow of fuel, being naturally expelled through the exhaust system. Idle memory reset error. You've probably experienced this yourself or know someone who has after performing basic maintenance like cleaning the throttle body or changing the air filter, only to find that the car now has an erratic idle. The RPMs fluctuate on their own, or the car revs up to 1,500 RPM when you stop at a traffic light. This happens because the engine control unit, the ECU, has a long-term learning memory, where it stored the values needed to keep the engine running when the throttle body was full of grease and dirt. By cleaning the metal, you've changed the physical reality of the incoming air, but the computer continues to apply the old electronic patches. The dealership will tell you that you need to connect their official diagnostic equipment to perform a forced idle relearn, charging you an exorbitant fee for a process that takes 2 minutes. The engineering trick to clear this error memory without special tools is a complete capacitor discharge via jumper wire. The procedure is as follows. Disconnect both battery cables, negative first, then positive. Once the cables are free and away from the battery terminals to avoid sparks, connect them together using a jumper wire or simply by touching them for at least 10 to 15 minutes. This forces all the internal capacitors in the car's computer to discharge completely, erasing the volatile RAM where the erroneous adaptive learning data is stored. Upon reconnecting the battery, the ECU awakens from a state of total amnesia and is forced to perform a real-time sensor scan. Detecting that the throttle body is now clean and allowing optimal airflow, it automatically recalibrates the idle speed to its factory settings within the first few miles of driving. The alternator voltage trick. This is a trick that borders on the illegal because it involves directly manipulating the vehicle's energy management. In modern cars, manufacturers have programmed alternators to charge at very low voltages, often around 13.5 volts, with the aim of reducing the mechanical load on the engine and saving an infinitesimal fraction of fuel to comply with emissions regulations. However, from a pure performance perspective, an internal combustion engine runs infinitely better when the electrical system operates between 14.2 and 14.5 volts. At this higher voltage, the ignition coil generates a much more powerful and hotter spark at the spark plug, ensuring that the mixture burns completely and quickly, extracting more energy from every drop of fuel. Furthermore, the injectors, which are solenoid valves, react more quickly and accurately to higher voltage pulses. In many vehicles, the voltage regulator decides how much to charge based on a reference signal from a battery temperature sensor or a sensing fuse called sense. The old-school tuner's trick is to insert a low-voltage diode in the signal wire going to the alternator. This diode creates an artificial voltage drop of approximately 0.5 volts in the signal received by the regulator. As a result, the regulator thinks the system voltage is lower than it actually is and tells the alternator to increase its output to compensate. That small increase immediately transforms the car's behavior, activating hidden functions via the engineering menu. Your instrument panel, however modern, is deliberately lying to you. Manufacturers have discovered that average drivers get scared when they see the coolant temperature gauge needle constantly fluctuating with traffic or inclines. Therefore, they've programmed the needles and digital gauges to stay exactly in the center, as long as the engine is within a safe range of 75 to 105 degrees Celsius. The problem is that by the time the needle decides to move into the red zone, the engine is already critically overheating. If you truly want to take care of your car, you need access to the real information the computer is reading. Almost all modern cars with digital displays or infotainment systems have what's known as the engineering menu or service menu. In models from the Volkswagen Group, Mercedes-Benz or BMW, it's accessed using button combinations that resemble secret codes, such as holding down the menu button for 10 seconds while turning the volume knob in a specific direction. Entering this mode unlocks a cascade of real-time technical data that would normally only be visible to a factory technician. You can see the exact engine oil temperature in degrees Celsius, the actual turbo pressure in bar, the precise battery voltage, and, most usefully, the actual digital speed captured by the ABS sensors, eliminating the 5% margin of error that all factory speedometers have to avoid fines. The precision handbrake adjustment. The vast majority of drivers, and unfortunately many inexperienced mechanics, attempt to adjust a loose handbrake by tightening the nut located under the lever inside the car. This is a serious technical error that will eventually damage the system. Adjusting from the lever only stretches the steel cables and unbalances the tension between the two rear wheels, and it does nothing to improve actual braking effectiveness. The true precision trick, the one old-school brake mechanics use to achieve a race-ready feel, is performed directly on the rear axle, where the friction occurs. Whether your car has rear drum brakes or disc brakes with a small internal auxiliary drum for parking, there is a mechanism called the star adjuster. The trick involves lifting the rear axle of the car, removing a small rubber plug located on the brake plate, and using a flathead screwdriver to manually rotate this internal star adjuster. The goal is to expand the brake shoes until the wheel locks completely, then back the adjustment exactly 3 or 4 clicks until the wheel spins freely again, but with a slight audible rub. By making this fine adjustment on both rear wheels, you not only give the handbrake a short, firm and professional feel, but you achieve something far more important. You align the brake shoes so that the service brake pedal reacts much higher and with a much more immediate bite. This happens because you've eliminated the dead travel of the rear pistons. It's the difference between a car that feels spongy when braking and one that has a powerful and balanced braking response from the very first millimeter of pressure on the pedal. Homemade thermal decarbonizing. This is perhaps the most dreaded trick for workshops that make a living from cylinder head repairs. Water injection is a technology that was used in World War II fighter planes to cool combustion chambers and gain extra power. However, in the world of survival maintenance, it's used to perform a deep internal cleaning that no chemical additive can match. The problem with modern engines, especially those with direct injection, is the accumulation of carbon deposits on the piston heads and valves. This carbon acts like a sponge, absorbing fuel and creating hotspots that cause pre-ignition, destroying the engine in the long run. The trick, which must be executed with surgical precision to avoid hydraulic shock, consists of introducing a very fine mist of distilled water through the intake vacuum system with the engine at operating temperature and at around 2,500 revolutions per minute. When water enters the combustion chamber at over 800 degrees Celsius, it instantly expands into high-pressure steam. This change of physical state creates a thermal shock cleaning effect that loosens the toughest carbon deposits, turning them into dust that is expelled through the exhaust. The oxygen sensor hack with a spacer. In 2026, emissions regulations became so stringent that a car's computer would illuminate the check engine light and limit engine power as soon as it detected that the catalytic converter's efficiency had dropped from 95% to 85%. A new, genuine catalytic converter could cost thousands of dollars, often exceeding the salvage value of a 10-year-old car. This is where the spacer or deceiver trick for the secondary oxygen sensor comes in, a practice many authorities consider illegal for tampering with emissions control systems, but one that saves entire family budgets. The downstream oxygen sensor has a single function: to verify that the catalytic converter is working. If the gases passing through it are too similar to those entering the system, the computer assumes the converter is dead. The trick involves installing a metal piece that moves the sensor away from the direct flow of exhaust gases, allowing only a small sample to come into contact with the sensor's tip. Being farther away and receiving less airflow, the sensor sends a clean gases signal to the control unit. This prevents the car from entering limp mode, allowing the engine to continue operating with its normal, powerful fuel injection map. It's a simple mechanical engineering solution that restores functionality to the vehicle when electronic bureaucracy tries to force you to retire it prematurely because of a part that, while not working perfectly, still allows the car to run flawlessly. The transmission oil trick in diesel engines. Modern diesel engines equipped with common rail systems are astonishingly precise machines, but they have an Achilles heel. Current diesel fuel has a very low sulfur content to comply with environmental regulations. The problem is that sulfur used to act as a natural lubricant for the high-pressure pump and injectors, which operate at pressures exceeding 2,000 bar. Without this lubrication, the metal components suffer dry friction wear, which eventually generates micro-metal shavings that destroy the entire injection system. The forbidden trick used by truckers who manage to get their engines past 1 million kilometers involves adding a precise proportion of two-stroke automatic transmission fluid, ATF, to the fuel tank, approximately 250 milliliters per 60 liters of diesel. This oil is designed to burn without leaving ash and has superior lubricating properties at high temperatures. When mixed with diesel, it creates a protective film on the pump plungers and injector needles, reducing wear and metallic engine noise. Although manufacturers warn that this can damage the particulate filter, the technical reality in 2026 shows that a well-lubricated injection system produces cleaner combustion that more than compensates for any oil residue. It's the difference between an injection pump that fails at 150,000 kilometers and one that lasts the entire life of the vehicle. Headlight restoration with vapor polymer. Forget supermarket polishing kits or toothpaste. Those tricks only last a few weeks before the headlight plastic yellows and becomes opaque again. The problem is that polishing removes the polycarbonate's original UV protection layer. The ultimate trick, which is considered dangerous due to the toxicity of its fumes if protection isn't used, is chemical acetone vapor polymerization. After sanding the headlight with fine 1000, 2000, and 3000 grit sandpaper to remove oxidation, a special heated cup is used to vaporize a liquid polymer. As the vapor passes over the plastic, a chemical reaction occurs that melts the surface of the polycarbonate and seals it with a new layer of clear, ultra-resistant polymer. The result is a factory finish with 100% optical clarity that won't degrade in the sun. Safety regulations in some countries attempt to restrict this method because it requires careful handling of chemicals, but it's the only real way to restore your car's full brightness without spending a fortune on new headlight units. It's an industrial-grade restoration process made available to the knowledgeable user who isn't afraid to get their hands dirty to see clearly in the dark. Thermal shielding of the intake system. Thermodynamics is simple. Cold air is denser and contains more oxygen, allowing for more fuel to be burned and more power to be generated. The problem is that engineers, to save space and costs, often place the plastic intake tubes right above the engine or near the radiator, where the air is heated before entering the cylinders. Every 10-degree increase in intake air temperature can represent a loss of up to 3% of engine power. The thermal shielding trick involves using high-temperature reflective aluminum tape or even thermal insulation used in the construction industry to wrap the entire intake pipe and air filter box. By creating this reflective barrier, you prevent radiant heat from the engine from preheating the air going into the combustion chamber. It is, essentially, a homemade cold air intake system that works as well as, or even better than, expensive $1,000 carbon fiber kits. In our workshop, we've measured intake temperature drops of up to 15 degrees Celsius after applying this shielding, resulting in a much more aggressive throttle response and an engine that doesn't lose power on the hottest summer days. It's a pure and free performance improvement that manufacturers ignore for aesthetic reasons. The late ring break-in procedure. We've reached the #1 spot with the most controversial yet effective trick in all of mechanical survival engineering. Many engines start burning oil not because they're destroyed, but because the piston rings have become glazed due to years of overly gentle city driving. When this happens, the rings don't seal properly against the cylinder walls, allowing oil to rise and compression to drop. The manual will tell you that you need a complete engine rebuild. However, there is a procedure called late or dynamic ring break-in. The trick involves changing the oil to a high-quality mineral-based oil, without excessive friction modifiers, and taking the car to a hilly road. With the engine at operating temperature, you must perform full acceleration from 2,000 to 5,000 RPM in third gear, and then, this is vital, release the accelerator completely and let the engine brake the car back down to 2,000 RPM. Repeating this cycle 10 or 15 times generates extreme positive and negative pressures within the cylinder, restoring the life and power that years of slow traffic had stolen. If you've made it this far, you now possess the knowledge that separates a mere driver from a true guardian of mechanics. We've broken down everything from transmission bits to the physics of piston rings, revealing tricks many would consider taboo, but which are nothing more than the pure application of science and experience over the manufacturer's commercial expediency.